We've talked a lot about linear transformations. What I want to do in this video, and actually the next few videos, is to show you how to essentially design linear transformations to do things to vectors that you want them to do. So we already know that if I have some linear transformation t, and it's a mapping from Rn to Rm, that we can represent t, what t does to any vector in x, or the mapping of t of x in Rn to Rm, we can represent it as some matrix times the vector x, where this would be an m by n matrix. M by n matrix. And we know that we can always construct this matrix, that any linear operation, any linear transformation can be represented by a matrix this way. And we can represent it by taking our identity matrix. You've seen that before. By taking the identity matrix with n rows and n columns. So it literally just looks like this. So it's a 1, and then it has n minus 1 zeros all the way down. Then it's a 0, 1, and then everything else is zeros all the way down. And so essentially you just have 1s down as diagonal. It's an n by n matrix. All of these are zeros, just like that. You take your identity matrix and you perform the transformation on each of its columns. On each of its columns. And we call each of these columns the standard basis for Rn. So this is column E1, this is column E2, and it has n columns, En. And each of these columns are, of course, members of Rn, because this is an n rows and n column matrix. And we know that A, our matrix A, can be represented as the transformation being operated on each of these columns. So the transformation on E1, and the transformation on E2, so forth, and so on, all the way to the transformation to En. And this is a really useful thing to know, because it's very easy to operate any transformation on each of these basis vectors that only have a 1 kind of in its corresponding dimension, or with respect to the corresponding variable, and everything else is 0. So let's, all of this is review. Let's actually use this information to construct some interesting transformations. So let's start with some set in Rn. And actually, everything I'm going to do is going to be in R2. But you can extend a lot of this into just general dimensions. But we're dealing with R2 right here. Obviously, it's only 2 dimensions right here. And let's say we have a triangle formed by the points. Let's say the first point is right here. Let's say it's the point 3, 2. 3, 2. And then you have the point, let's say that your next point in your triangle is the point, well, let's just make it the point minus 3, 2. I shouldn't have written that as a fraction. I don't know why I did that. 3, 2. Then you have the point minus 3, 2. And that's this point right here, minus 3, 2. And then let's say, just for fun, let's say you have the point, let's say we have the point, or the vector, the position vector, right? 3, minus 2. 3, minus 2, which is right here. Now, each of these are position vectors, and I can draw them. I could draw this 3, 2 as in the standard position by kind of drawing an arrow like that. I could do the minus 3, 2 in its standard position like that. And 3, minus 2 I could draw like that. But more than the actual position vectors, I'm more concerned with the positions that they specify. And we know that if we take the set of all of the positions, or all of the position vectors that specify the triangle that's essentially formed by connecting these dots, the transformation of this set, so we're going to apply some transformation of that, is essentially you take the transformation of each of these endpoints, and then you connect the dots in the same order. And we saw that several videos ago. But let's actually design a transformation here. So let's say we want to, let's just write down in words what we want to do with whatever we start in our domain. Let's say we want to reflect around the x-axis, reflect around the, well, actually, let's reflect around the y-axis. Around the y-axis. So we essentially want to flip it over. We want to flip it over that way. So I'm kind of envisioning something that'll look something like that. when we flip it over. So we're going to reflect it around the y-axis. And let's say we want to stretch in y direction by 2, in y direction times 2. So what I envision, we're going to flip it over like this, what I just drew here. And then we want to stretch it. So we're going to first flip it. That's kind of step 1. And then step 2 is we're going to stretch it. So instead of looking like this, it'll be twice as tall. So it'll look like this, without necessarily stretching the x. So how can we do that? So the first idea of reflecting around the y-axis, right? So what we want is this point that was a -3 in the x-coordinate right there. We want this point to have its same y-coordinate. We want it to still have a 2 there. And I'm calling the second coordinate here our y-coordinate. I could call that our x2 coordinate, but we're used to dealing with the y-coordinate when we graph things. So I'll just keep calling it the y-coordinate. But what we want is this -3 to turn to a +3. And because we want this point to end up over here. And we want this +3 here to end up becoming a -3 over here. And we want this +3 for the x-coordinate to end up as a -3 over there. So as you can imagine, all we're doing is we're flipping the sign. When this reflection around y, this is just equivalent to flipping the sign of the x-coordinate. So this statement right here is equivalent to -1 times the x-coordinate. So let me call that, or let's call that times x1, because this is x1. x1. And then stretching in the y direction. So what does that mean? That means that whatever height we have here, so this next step here is whatever height we have here, I want it to be 2 times as much. So right here, this coordinate is 3, 2. If I didn't do this first step first, I would want to make it 3, 4. I want to make 2 times the y-coordinate. So the next thing I want to do is I want to do 2 times, well, I could either call it, well, let me just call it the y-coordinate. And it's a little bit different convention than I've been using, but I'm just calling these vectors. Instead of calling them x1 and x2, I'm saying that my vectors in R2, the first term I'm calling the x term, or the x entry, and the second term I'm calling the y entry. But it's the same idea that we've been doing before. I'm just switching to this notation because we're used to thinking of this as the y-axis as opposed to the x1 and the x2 axis. So how do we construct this transformation? I mean, I can write it down in kind of transformation words. I could define my transformation as t of some vector x, or let me write it this way. T of some vector xy is going to be equal to, I want to take -1 times the x, so I'm going to minus the x, and then I'm going to multiply 2 times the y. So that's how I could just write it in transformation language, and that's pretty straightforward. But how would I actually construct a matrix for this? So what you do is you just take we're dealing in R2, so you start off with the identity matrix in R2, which is just 1, 0, 0, 1. And you apply this transformation to each of the columns of this identity matrix, to each of the columns of that identity matrix. So if you apply the transformation to this first column, what do you get? So what we're going to do is we're going to create a new matrix A and say that is equal to the transformation of, let me write it like this, transformation of 1, 0. That's going to be our new column. We're just going to transform this column. And then the second column is going to be the transformation of that column. So it's transformation of 0, 1, just like that. And so what are these equal to? The transformation of 1, 0. So let me write it down here in green. So A is equal to, what's the transformation of 1, 0, where x is 1? Well, we just take the minus of the x term, so we get -1, and then 2 times the y term. So 2 times 0 is just 0. Now do the second term. The minus of the 0 term is just -0, so that just stays as 0. And then you multiply 2 times the y term. So 2 times y is going to be equal to 2 times 1, so it's equal to 2. So now we can describe this transformation. So now we could say the transformation of some vector xy. We can describe it as a matrix vector product. It is equal to minus 1, 0, and 0, 2 times our vector, times x, y. And let's apply it to verify that it works, to verify that our matrix works. So this first point, and I'll try to do it color-coded. Let's do this first point right here. This is minus 3, 2. So that's minus 3, 2. So what is minus 3, 2? I'll do it right over here. I could just look at that. So what is minus 1, 0, and 0, 2 times minus 3, 2? Well, this is just a straight up matrix vector product. Minus 1 times minus 3 is positive 3, plus 0 times 2. So plus 0. So this is 3. And then 0 times minus 3 is 0, plus 2 times 2. So it's 3, 4. So that point right there will now become the point 3, 4. It now becomes that point right there. Let's look at this point right here, the point 3, 2. So let's take our transformation matrix, minus 1, 0, 0, 2 times 3, 2. This is equal to minus 1 times 3 is minus 3 plus 0 times 2. So it's just minus 3. You have 0 times 3, which is 0, plus 2 times 2, which is 4. 0 plus, so you get that point. So this point, by our transformation t, becomes minus 3, 4. So minus 3, 4. And I kind of switch in my terminology. I say it becomes, or you could say it's mapped to, if you want to be kind of use the language that I use when I introduce the ideas of functions and transformation. This point is mapped to this point in R2. And then finally, let's look at this point right here. Apply our transformation matrix that we've engineered. Let's multiply minus 1, 0, 0, 2 times this point right here, which is 3 minus 2. 3 minus 2, which is equal to minus 1 times 3 is minus 3. And then 0 times minus 2 is just 0. So this becomes minus 3. And then 0 times 3 is 0. 2 times minus 2 is minus 4. So minus 3, minus 4. So this point right here becomes minus 3, minus 4. Becomes that point right there. And we know that the set in R2 that connects these dots by the same transformation will be mapped to the set in R3 that connects these dots. We've seen that already. I think that was 3 videos ago. So the image of this set that I've drawn here, this triangle is just a set of points specified by a set of vectors. The image of that set of position vectors specifies these points right here. Specifies the points that I'm drawing right here. Let me see if I'm doing it right. There you go, just like that. And lo and behold, it has done what we wanted to do. We flipped it over so that we got kind of this side onto the other side like that. And then we stretched it. And we stretched it in the y direction. And we see that it has stretched by a factor of 2. We flipped it first, and then we stretched it by a factor of 2. And in general, any of these operations can be performed. I mean, you can always go back to the basics. You can always say, look, I can write my transformation in this type of form. Then I can just apply that to my basis vectors, or the columns in my identity matrix. But a general theme is any of these transformations that literally just scale in either the x or y direction, and or essentially just, well, you could say scale. They could either shrink or expand in the x or y direction, or flip in the x or y direction, creating a reflection. These are going to be diagonal matrices. Diagonal matrices. Diagonal matrices. And why are they diagonal matrices? Because they only have non-zero terms along their diagonal. This is a 2 by 2 case. If I did a 3 by 3, it would be zeros everywhere except along the diagonal. And it makes a lot of sense because this first term is essentially what you're doing to the x1 term. The second term is what you're doing to the x2 term. If you had, or the y term in our example, if I had multiple terms, this was a 3 by 3, that would be what I would do to the third dimension. Then the next term would be what I would do to the fourth dimension. So you could expand this idea to an arbitrary Rn. But anyway, this whole point of this video is to kind of introduce you to this idea of creating custom transformations. And I think you're already starting to realize this could be very useful if you want to do, especially in computer programming, if you're going to do some graphics or create some type of multi-dimensional games.